Hey everyone, let's start. So, welcome to this talk by Siddharth Bhat. He's going to talk to us about equality saturation. So, Siddharth, trying to take it away.
So hey everyone. I'll be discussing a paper that was published this year at Purple. The paper is called Egg, Fast and Extensible Equality Saturation. So essentially, I hope to sort of like give a sense of what equality saturation is and why someone would want to use the library that they build in this paper, it, it, for their needs when they choose to write a compiler. So the library is called Egg, which stands for E graphs good. And the library performs this thing called equality saturation. Let's get into it and let's learn what it does. Um, right. So I guess the starting point for all of this is to essentially it is to first have a sense of what a compiler does, or like how a compiler actually manages to optimize the program. So let's take this like program which sets x to 1, and and it then compares whether x is 1. If it's 1, it prints foo, otherwise it prints bar. Now ideally at the end of our optimization, we would like this function to optimize to a function that simply says print foo, right? Because there's an assignment, and it checks if the number 1 equals 1 essentially. So the way in which compilers usually do this is they run a sequence of improvements on your original program in the hopes of simplifying it. So, for example, one thing a compiler might do is to simply attempt to eliminate constants. So here we set x equals 1, and then right after we check whether the variable x equals 1. So rather than doing that, we can propagate the constant 1 and thereby get the expression if 1 equals 1. So this program is slightly simpler than the previous one. Now the next thing we might do is to try to perform algebraic simplification or canonicalization, as it's also sometimes called. So we know from like whatever algebra that 1 equals 1 is always true. So essentially we can sort of like simplify this expression into this expression that we have here. And finally, what we can then do is to attempt to simplify control flow. So we have an if true and then an else. So it's clear that if you have such control flow, it's equivalent to this type of control flow, where the control will only flow into the then branch and will never flow into the else branch. So by performing these three extremely simple steps, we've managed to simplify this program into this program. So the general idea is that no step needs to be smart, right? So like this step of converting if true to this is like really dumb. And similarly, the step of like knowing that when x equals 1, x is 1 is also really dumb. And similarly, knowing that 1 equals 1 is true is like really dumb. But then like when you run these really dumb passes in sequence, something nice might happen, and you might be able to make like a sort of non-trivial transformation here. So that's the general structure of how a compiler works. So the way in which you'd imagine it is you have an initial program T0, you apply some tiny improvement T1, which gives you a slightly improved program T1, to which you apply a tiny improvement T2, which gives you a slightly improved program T2, and then after like doing hundreds of these things, you'll finally end up at like an optimized program. Right, but the question now is, in what order do we run these transformations, right? So here it is like I chose a sort of Goldilocks order where we did this and then we did this and then we did this and it all worked out. So does this always work? Well, let's find out. So let's consider two programs, one called foo and one called bar. So they're pretty similar. So they both try to check a condition and they try to print foo or bar. But the only difference is that in bar the way in which the value of the variable is computed is different. So here we compute int y equals 42 double equals 42. So here let's try to like rerun the exact same order of optimizations we had before. So first let's try constant propagation. Now here, because x was a constant, it gets propagated here as a 1. So we get 1 equals 1. But here on this side, because like y is not a constant, it hasn't been simplified yet. So it's still like an expression. It's not a constant. We don't know that it's a constant. It doesn't get propagated. So nothing happens here. Now next, when we attempt to simplify or canonicalize, here 1 equals 1 becomes true, while here the expression x equals x simplifies to true. And then finally, when we try to simplify control flow, here once again we had an if true, and that gets simplified. But here we have an if while, and that doesn't get simplified. Even though we know that y equals true like above, the compiler doesn't know that. It simply tries to pattern match on the pattern if true. Yeah, and because this does not like obey that pattern, this doesn't get simplified. Yeah, so does anyone have any questions so far? Oh, and feel free to interrupt me if you do, by the way. So I'm pausing for questions now, if there are any. Okay, so I'll take that as a no. Right. So yeah. So in some sense, it's sort of clear that that essentially like trying to run things in the same order isn't going to work, because an order that might work well for one program might not work well for another program. Um, Now the sort of like classic way to actually overcome this is to simply rerun your transformations over and over. So in this case, let's focus on bar. So we started with bar. We first run constant propagation, which is like useless, like nothing actually gets simplified. And then we run canonicalization, which manages to simplify this. And then we run control flow simplification, where again nothing happens. But now what we can do is to simply like rerun the same passes again. So if I were to now rerun constant propagation, which ran on step 1 and is running again on step 4, it then manages to propagate the simplification that happened here to here. And then finally in step 5, when we run control flow simplification again, so we're running this transformation twice, we get the final optimized program. So the reason this was sort of possible is that like we took the same transformation and we ran it like multiple times, so the transformations could sort of like iterate and improve upon each other. Um, and like this is not some sort of like hokum whatever example. This is what's actually done in a modern compiler, and this problem of in which order to run transformations is called as the phase ordering problem, and sort of like repeatedly rerunning your transforms is a pretty popular solution. Yeah, so for example, we can ask Clang, hey Clang, what passes do you run when I ask you to optimize the program at O3 on some arbitrary C file? And it spits out like this huge list of passes at you, which is like not very enlightening. So let's try to like focus on some of the passes that it runs. Yeah, so like just sort of like blanking out everything else, we can see that it runs this pass called inst combine a bunch of times. Inst combine is the sort of canonicalizer or the simplifier. Inst combine stands for instruction combine. Yeah, and then similarly, it also like runs another pass called simplify CFG, which is responsible for simplifying control flow. Yeah, and like as we can see, it essentially like runs these two passes a lot of times, hoping that the types of simplifications that we saw before do happen. Yeah, and like so this is like really done in a modern production compiler. This type of solution to the phase ordering problem. Yeah, so any questions? Okay, right. But now, like, is this really a solution, right? Like, does simply like just rerunning the transforms you have over and over actually work? So let's take like an example to see whether it actually works or not. So let's just consider a simple arithmetic expression where we have a times 2 first divided by 2. So that's what the brackets are for. Now, one way to optimize this would be to take the a times 2 and to rewrite it into a left shift 1 divided by 2. And another way to like sort of start optimizing this program is to take the a times 2 divided by 2 and to reassociate it and to sort of like reorder the expressions and to write as a times 2 by 2. Right? This is like a valid rewrite that one can do on an arithmetic expression. But then, in some sense, this gives us opportunities to make more progress, because once we have 2 by 2, we know from arithmetic that it's equal to 1, and then we get a times 1, so we can pattern match an a times 1, and we can simplify the entire program to a. But then like if we look at this program here, we're sort of stuck in that like, okay, I mean, we've managed to maybe make the multiplication run faster, but then we haven't actually managed to simplify this program to the sort of like the smallest size possible. And worse, sort of like the problem is that once we run an a, it now looks like this. And once it looks like this, we can't actually run a b anymore, because b tries to pattern match on a pattern that looks like a times x divided by x. but this looks like A left shift 1 divided by 2. So the pattern that corresponds to B doesn't actually work anymore. And so we're blocked. Um, yeah, so in some sense, like the actual like problem is that these transformations like fail to commute. Like running an A inherently blocks a B, and similarly running a B inherently blocks an A. Um, and so like our previous solution of rerunning like A and a B and an A and a B won't work anymore, because like running one of them just blocks the other one. Right? Yeah. So these passes sort of interfere with each other. So, but then like okay, we can then say fine. In which case, I'm not actually going to like modify the program. So rather, I can start with A times 2 divided by 2, and then I can run an A. And now when I run an A, I keep both the old program, which said A times 2 divided by 2, along with A left shift 1 by 2, right? So I keep both pieces of information here. I don't actually destroy the old program that I had. So now at this point, I can actually run a B. And the reason I can run a B is that I have both the A left shift 1 by 2 as well as the A times 2 divided by 2. So now that I have both, so B can look at this part and it can go, oh look, there's an A into 2 divided by 2. So I'll just convert it to a A into 2 by 2. So now we're no longer actually storing programs, but we're sort of storing collections of programs that are equivalent to each other. So we started with this single program. We ran an A and we got these two equivalent programs. We then ran a B and we now got these three equivalent programs. So now after this, so now like we can sort of continue our simplification story, and we can simplify A into 2 by 2 to A into 1 using the same rewrite as before. And then finally we can simplify the A into 1 with A. So the advantage of sort of like never deleting the old program, but simply like storing both the old and the new program is that now is that now like the ordering doesn't matter because we never destroy any information. But like of course the problem with this is that essentially like this can get pretty large, right? Because you're literally storing like entire copies of programs. So the point of equality saturation is this: it's to never actually rewrite. It's to never actually like modify a program. It's to simply sort of like add equalities to the same program. But you don't store it this naively. It's like but like you don't sort of simply store copies of the program, but you sort of attempt to store all the different variants of a program in a sort of optimized fashion, or like in a space efficient fashion. Um, and this like actually is a solution to the problem. Um, so questions?
So, Siddharth, there are questions on the chat. I
Okay.
can summarize the questions that are there so far. So,
Yeah.
Ishwan had asked, can priority ordering between applying the rules solve this problem? And he
Mhm.
had asked, can we run the iteration multiple times until there are no differences between two consecutive iterations? And solve.
In yeah so right s- hmm. yeah So with respect to like running, so like with respect to sort of rerunning it multiple times till there are no changes. We do this, but then like if you look at this case, it's like after we run an A, like there is no more progress we can make, because like we can't actually run the B or the other transforms we have. But in some sense, this is not the best program we could have achieved. The best program we could have achieved is this particular A that we had. So right. So like rerunning the transforms till we don't get anything new is a valid strategy, but then that sort of begs the question of like even while I rerun, in which order do I rerun? And as for prioritizing like the different transforms, then you sort of like punt the problem into, okay, how do you design a good ordering for the different passes? And as far as I know, like nobody has a good solution for any of these. Because they're inherently like complicated problems. Yeah. So at least I think in LLVM, what people try to do is they like try a bunch of different orderings on the benchmarking suite, and they pick the ordering that works best. So the problem is like in some sense, if you have n different passes, there are like n factorial permutations. So the problem space is like quite large. Um, yeah, if you attempt to like try to provide priority or something like that. Yeah. So any more questions? And like, does that help?
So this can be visualized as a breadth-first traversal, like a graph full of equivalent programs, and we were traversing breadth-first search, like over.
Yeah, yeah, that's yeah. Sort of. Yeah, pretty much. So I'll show like running this process on like on the same program later on with like visually. That might make it slightly more clear. But yeah, um, cool. So uh, more questions, or do I move on? Okay. I'm going to continue. Um, Right. Yeah. So the solution is to sort of like run all the passes in parallel while only maintaining equalities, and you therefore like never actually modify a program. So classically, you would have a program, you run T0, you get T1, you run transformation T1, you get T2, and so on. Um, but like you really want to explore the space of all possible transformations, but that's sort of hard. So rather, what you do is you just like you have the program and you just try to like add equalities onto the same program. So this is sort of the equality saturation solution to this particular problem. Um, right. So let's like actually sort of take the concrete example and let's try to like understand how equality saturation runs and what data structures it maintains. Um, so this is the same program that we had. It was a into 2 divided by 2. I'm going to like write it in Lisp notation because like that makes actually drawing the abstract syntax tree easier. So I write it as like divided by multiplication of a2 and then a 2. So the divided by is the root node, and on the left hand side we have a multiplication. This is the a times 2 part, and this is the divided by 2 part. Now, already one thing that we should notice is that essentially, like both this two in the multiplication and this two in the division point to like the same node in the tree. Yeah, so essentially um, we deduplicate all the nodes, and yeah, and so like we only have one copy of 2 or one copy of a or one copy of a times 2 or whatever. Um, yeah. So this is like the basic data structure that will be manipulated.
Siddharth, if we
Yeah.
deduplicate the nodes, then if
Yeah.
there is some edges out of two, then how would we know, like if there is an edge out of two, like so maybe
Yeah.
some two edges out of two,
Yeah. Yeah. Yeah.
then, how would we pass that?
Yeah. Right. Yeah. So yeah. Exactly. Uh, yeah. So whenever we deduplicate a node, we're sort of deduplicating the entire like subtree under that node. Yeah. So you're right that like if the two like actually had edges, then we would need to make sure that like that we were deduplicating the entire subtree under two, and we're not just deduplicating like two. But here, because it's a leaf node, we're fine. Yeah, we know that two is two. But yeah, in general, we try to deduplicate subtrees. Um, right. So we start with this program, and now remember that like the first equality that we like tried to rewrite with was to say that a times 2 is the same as a left shift 1. So the general pattern was we had a p times 2 and we converted it into a p left shift 1. So and when we instantiate this pattern on a times 2, uh, what we need to do is we need to insert new nodes that represent the idea of like a left shift 1. So that causes us to add a left shift node, add a 1 node, and the left shift node like points to the a node because it's a left shift 1. And we also need to track that a times 2 is the same as a left shift 1. So that's the little tilde that you see here. That's the equality. And in the diagram, the equality is represented by the dotted lines that we have between the star subtree and the like left shift subtree. So this is telling us that the entire subtree a times 2 is equal to the entire subtree a left shift 1. Um, yeah. So questions at this step as to what we did? Okay. Um, right. So notice that like we still have the old subtree, the a times 2 thing. We've just like added new nodes to represent a left shift 1, and we've added an equality between the star subtree and the left shift subtree. Yeah. So next what we can do is we can use the rewrite rule that says that p times q divided by r is the same as p times q divided by r. So this is like the general pattern. Um, and yeah, and now we're going to instantiate it on the a times 2 divided by 2. So p will be a, q will be 2, and r will be 2. Yeah, so once again, like we need to do the same thing. We need to create new nodes, and then we need to add equalities. So yeah, so the first thing we do is we add new nodes for like a times 2 divided by 2. Oh, this is a slash, not a 1. A times 2 divided by 2. So like this subtree represents a times 2 by 2. And the pink dotted line circle represents the fact that this entire subtree is equivalent to this entire subtree. Yeah, I questions? Okay. Yeah, and now the next thing that we can rewrite by is the knowledge that, well, x by x is equal to 1 for any choice of x. So here we have a thing that looks like x by x. We have a 2 divided by 2 here, which is like this subtree, the divided by with the 2 and the 2. And so all this rewrite does is it adds an equality between this subtree and the node 1. So yeah, so like this rewrite is interesting because this rewrite doesn't actually add any new nodes. It simply reuses the old nodes and it adds an equality between the expression 2 divided by 2 and the expression 1. Um, yeah, right. So then finally we know that x times 1 is the same as x. um, yeah, so right, so notice that like, so we have x times 1 where 1 is represented by divided by 2 2, and x is represented by the a, and the star is the outer star node. So this is x times 1, and we want to say that this is equal to x or this is equal to a. So this too adds a new equality, where we say that okay, this entire multiplication subtree becomes equivalent to this leaf node. Questions? Okay. Yeah, so now like this equality is again like once again interesting, because if we like only try to focus on this equality, then essentially we have the star from here, we have the a from here, and then we have the divided by 2 2 or whatever, but we know that the divided by 2 2 is equivalent to 1 by the purple equality. So therefore we can just write the right hand child of the star as a 1. So this subtree represents a times 1. But then, in some sense, we know that a times 1 is, we know that a is equivalent to this entire subtree. That's the golden colored relation we added like just now. So what I can do is to then expand this out based on the new relation that I just added. And that lets me represent a times 1 because this subtree is equivalent to this node. So I can replace this node by the subtree itself. So I know that a times 1 is equivalent to a times 1 times 1, but I can repeat the same process is equivalent to a times 1 times 1 times 1, and so on. So in some sense, the reason equality saturation actually gets its power is that like because it can sort of add these arbitrary equalities, it can also represent these types of cyclic equalities, where you can represent like an entire infinite collection of equalities that a is equivalent to a times 1 is equivalent to a times 1 times 1 is equivalent to a times 1 times 1 times 1, and so on, within like the same graph, which is something you don't generally do in a normal compiler.
So this is like a nested data structure, like a list can represent any length, a list of any length. Right. So it's
Yeah, exactly. Yeah, so like if I had to compare it to something, I would probably compare it to like the thing in GHC where we say let x equals 1 colon x. So in some sense, like this x is 1 followed by itself. So if you try to force it, you'll just like get an infinite sequence of ones. So it's the same idea here, where you're saying that like this tail is equivalent to itself, so you can expand it out as many times as you like. Um, yeah, so it's exactly the same trick as building an infinite list uh, within Haskell using laziness. Um, yeah, so yeah, it's like that's sort of the central idea. But like this finite equation captures an infinite like sequence of things, um, because you can like write down the recursion, or like because you can say that you can repeat the name. Similarly here you can actually say that this is equivalent to this. uh, yeah, did that help?
Yes. Yeah.
Yeah,
That was good.
okay. More questions?
Hello, can you
Yeah,
hear me?
yeah, I can.
I understood what you said about it expanding, but why would an expanding data structure help you in optimizing? You would want it to contract, wouldn't it?
uh,
Smaller is better, no?
yeah, so I mean like yeah, I mean I don't know of like any good examples off the top of my head. But I mean but like so okay, like I mean okay, so like I don't know, like I mean you might have some sort of a really weird architecture, where like multiplication takes 4 clock cycles and addition takes 1 clock cycle. So maybe it's actually advantageous to know that x times 3 can be written as x plus x plus x. So even though x plus x plus x is like larger than x times 3, it's still faster to execute. Um,
Yeah, so I think maybe we can say it like this: like maybe there is a transformation which would work on the left side, which would have more impact, like which would reduce the running time when compared to the right one.
yeah, and right, and yeah,
Maybe
and
there might be a transformation. We don't know. So
yeah, exactly, and also like a compact representation need not be the fastest way to actually run it on hardware. That's what happens in the x plus x plus x case. Like it's more code, so it's a larger subtree, but it runs faster. um, yeah, so yeah, does that help?
Yeah.
Okay.
Thanks. Got it.
Hmm. So any more questions? Right. Okay. Yeah. So this particular data structure that actually maintains these equalities is called as an E-graph. I think it's E-graph or equality graph. And essentially, yeah, and the entire point of the paper is to like write a library that lets you easily use these E-graphs to write a compiler. And they have some like case studies. So I'm going to like now explain one of the case studies. Yeah, and then we'll see where to go from there. Um, Right. So in some sense, like the actual ideas involved in this are to have the notion of nodes, which are like these leaf nodes and these interior nodes that we have, and a notion of equalities, which we like add into the thing, and a notion of like the set of all expressions that are like equivalent to each other. Like this division is equivalent to this multiplication is equivalent to this A. So that's the equivalence classes thing, which I've written in black, pink, and gold, because the black is the original expression, the pink is the expression in terms of the multiplication, and the gold is the final optimized expression where we just have an A. Yeah, right. So this library essentially lets you uh, maintain and modify this data structure and easily add equalities and rewrite into it. Um, yeah. So one of the things that they use to evaluate their thing is a library called Herbie. Um, so so essentially what Herbie does is it sort of like inspects your code, and it tries to like rewrite bad floating point expressions into good floating point expressions. Um, where by bad they mean that like the expression is inaccurate, and by good they mean that the expression is like floating point accurate for all inputs. And like, yeah, once again, they choose to use equality saturation simply because, like as in the left shift and multiplication example, and like in general, when you try to simplify like mathematical expressions, it's really unclear which steps you should take first and which steps you should take next. So it makes sense to simply like try to sort of like try all steps you can. So that's why they use equality saturation. So in this particular case, for example, like these are the sets of rewrites that you need to take, where you need to multiply and divide by like the same expression to cancel stuff out, and yeah, like it works out. You get LHS equal to RHS. Um, right, and they choose to use equality saturation. So their original implementation is in Racket, which is like, yeah, whatever, which takes this much time. And the final implementation that uses the library uh, is like 4 orders of magnitude better. So the graph is log scale. So this is like 10 to the 1, this is 10 to the 4. Yeah, so essentially, like switching from a handwritten implementation in Racket to a fast implementation in Rust, along with some algorithmic improvements that they suggest, gives them like a 4 order of magnitude improvement. Yeah, which like pretty strongly makes their case that like perhaps you can actually write production compilers using this technique. Um, yeah. Right. And okay, and so like one of the sort of like problems in trying to use this equality saturation is that like whenever I've been sort of describing these equalities, it's like they've always been algebraic identities, right? Like p star 2 is always equivalent to p left shift 1, or like p times q by r is always equivalent to p times q by r. So they're sort of syntactic. But then like usually when you want to do anything sophisticated in a compiler or even in a tool like Herbie, it's usually never going to actually be syntactic, because like for example, let's consider an expression x by x, which like if you have floating point numbers, it's going to equal 1 when x is not equal to 0, and it's going to equal not a number when x equals 0. So the way in which compilers like usually attempt to handle situations like this is they first attempt to like analyze the program. So like consider a program where you do 1 plus 2 divided by 6 minus 3. Yeah, so a compiler would first like attempt to analyze it, telling it that it's equal to this subtree evaluates to 3 and the right subtree evaluates to 3, and it gets a 3 by 3, and that becomes equivalent to 1. And similarly, on the right hand side, it's a 1 minus 1 divided by a 6 minus 6. So a compiler would traditionally analyze it, it would figure out it's a 0 by 0, and it would conclude it's none. And right, and the interesting thing about the egg paper, and that I'm not really going to go into here, um, is that they provide a way for you to write these sorts of rewrites where you not only like just blindly rewrite according to equalities, but your rewrites in fact actually collect information as they rewrite things. So one of the things the paper provides is it lets you do both analysis and rewrite on the same data structure, which was something that like wasn't really available before. Um, yeah, and that actually makes the thing applicable to writing compilers, because often in a compiler your rewrites are going to look like this, where they're not purely syntactic, but they also need like access to semantic information. And the egg like theory actually lets you access the semantic information. um, yeah, and that's something that's nice about the paper. Right, so yeah, so now the next thing that we'll go into is like one type of speed up that they managed to like yeah, that they managed to like show how to achieve. Yeah, so earlier whenever people used to implement equality saturation, they used to implement it something like this. So let's imagine we have a root node f1 which has a node f2 under it, which has a node dot dot dot, which has a node fn under it, which has a child called x, and then you have other nodes called y1, y2 up to ym. And now in general, for you to like actually check for equalities of like entire subtrees as we had to, you would in general maintain some sort of a hash. So if you imagine that these are the hashes of all of the different nodes, and these are the hashes of all the different nodes. Right. So yeah. So now let's say that you ask the library that to assign x to y1. And so when you ask it to assign x and y1, well, what's going to happen? We need to recompute all the hashes, because now we want the hashes to know that x is indeed equal to y1. So the hash of x changes to kb, the hash of y1 changes to kb. But if x changes, then so should its parent. So then this changes to kc. But if fn changes, its parent should also change. So that changes to kd, and so on up to f1. Um, right, and next maybe you say, okay, let x be equal to y2. Yeah, and right, and so when you say x equals y2, well, again the exact same thing happens. All the hashes need to change starting from y2 all the way up to the parent. So you can see where this is going. We keep doing this, and when I say x equals ym, once again all the hashes change. So for each equality that we assigned of x equals y1, x equals y2 up to x equals ym, we changed like n nodes here. So that's n into m amount of work. So rather what they do in the equality saturation is they essentially choose to do this lazily. Um, so yeah, so in their paper, it's like they don't instantly recompute the hashes. So you might first say x equals y1, it says okay. You might then say x equals y2, it says okay. You might then say x equals ym, it then says okay. And then finally, when you actually ask it, hey, is x equivalent to someone else, will it then like actually recompute all the hashes? Yeah, but now like because it has all the information up front, um, it essentially just needs to like rewrite all the hashes in one shot. So all of these become the same hash, and then fn changes, f2 changes, up to f1 changes. So that's like n plus m work. Um, and essentially the reason they actually like get this performance improvement is they sort of batch the work that they do. Yeah, and that's what like actually manages to give them this like whatever quadratic to linear performance improvement. Yeah, questions? Okay. Yeah, so that's sort of like the point of the paper. Yeah, and right. So yeah, so at least for me, the takeaways were that like that this particular technique of simply like rewriting with equalities actually works. And yeah, and sort of like you can in fact like try to rewrite with all equalities at once, as long as you like maintain the data structure in a reasonably smart way. um, yeah, and they have like a good API that lets you use it. uh, yeah, so like I think that concludes my talk. At least I wanted to like give a general idea of what the paper was about. um, yeah, so thanks guys. uh,
Thanks, Siddharth. Are there any questions for Siddharth? Um, so, Siddharth, so I had, it's not a question as such, but
right.
to understand this library,
Yeah.
so this is going to be Rust code, right? So,
Yeah.
but is there like an algorithmic implementation of this algorithm just to understand it, not to actually use it? But, is there something that we can look at?
No, not no. Like I think it's only the Rust library that like actually has all the implementation.
So if
So
you want to understand the guts of this, that's the library to look at.
yeah, you'd have to look at the library. Although like I would be interested to like write a sort of prototype implementation of the library. So like if you're interested, we could do it together.
Yeah, that would be great. I think definitely that would make it clearer. It may not be as fast as Rust's implementation.
Right.
It would be great from an understanding perspective.
Yeah, I agree. Yeah.
Okay. Great. Thanks, Siddharth. Thanks for your time.
Cool. Thank you.
I just had one question
Mm-hmm.
actually. So I just realized that this library was just offering a way to do all the to do all of the compare all of the orderings at the same time. But how would someone write a cost function for this and figure out which of the actual comparisons is the most efficient one?
Yeah. So
I'm talking from a usability perspective, like apart from library, how would someone use it?
Like, are you referring to in terms of like how you would actually use the library, or um,
No, I mean logically,
yeah,
if you have a list of all sorts of states, then how would
yeah,
you decide which one is the best one?
yes. So I can show that to you. Yeah. So right. So okay. So essentially, what you do is that, like, when you want to finally like extract out a program, um, given like you have the entire collection of equalities, what you then do is you one sec. Yeah. So essentially, what fine. Okay, yeah. So the idea is that you have this whole mess of like programs that are equivalent. How do you like actually extract out the program that is best? So at least what they do is they try to like find a program that is smallest in terms of subtree size. So in this case, if you look at it in terms of subtree size, the program that only computes a like is going to be the smallest, because the tree only corresponds to a single node. So that's the heuristic that they have. But like in general, the idea is that, like, because your library can do analysis of all the like subtrees that you have as well, you can write any analysis that you want, which in some sense like tries to assign a cost function to every subtree. And the library will extract out to you the program that has the best cost function, that minimizes the cost function. um, yeah, but at least in all of like their test programs, they just use subtree size as a proxy for this. So that did that answer the question?
Yeah, that did.
Yeah. So
Has
I. Mhm.
has anyone tried to apply this to a mainstream programming language like PureScript or Haskell, like a functional? I'm assuming this applies better to functional programming languages, but
Yeah, so I mean, so there were a series of papers in like 2011 or something called Equality Saturation, a new approach to optimization. And I think they tried to optimize Java, and like they had reasonably good results. But like again, for them the problem was like the algorithm was too slow. But now that this new library exists, maybe like people will like try again. But at least in their paper, they've only tried it on things like Herbie and some other CAD programming language or whatever. They haven't tried it on like a real world language yet. Um, yeah.
I see. And when you say that it's faster, this library is faster, is it
Yeah.
because the earlier algorithms were doing rerunning multiple passes of the same series of steps, or why is this particular library faster?
Yeah, so my understanding of why it's faster, based on what they claim, is one is because of like this particular algorithmic improvement, where they sort of like where they try to batch all the like rewrites that can invalidate the AST at once, and then they revalidate all the nodes, and then they check equalities. So this gives them like a pretty large improvement in performance. And also their claim is and also like their claim is that like before, whenever people tried to do equality saturation, it was like there was no good way to actually write an analysis for this thing. um, by an analysis, I mean like the semantic rewrite case. So people did lots of ad hoc things, but then like in their implementation, it's quite clean to actually do these analysis. So parallelizing the actual implementation became really easy for them. So if you look at like their actual Rust implementation, um, I believe it like does all the rewrites in parallel as well. So they have like both sort of engineering improvements, where they like store the data better and they parallelize and things like that, and they have algorithmic improvements in terms of asymptotics. And so this like actually makes them much faster than anyone else. Yeah.
There was a Racket implementation, right, where the initial results came from.
Yeah, and their library is four orders of magnitude faster, right? That's like 10,000. Oh no, 1,000. Yeah, that's like that's 1,000x faster. Yeah.
So was the Racket implementation So with the same algorithm that we are seeing in egg, or was it a different algorithm that was slow? It's not
Yeah,
the engineering thing, right?
right, so okay, yeah. So if you see the plus batching plus rebuilding, so these are the algorithmic improvements, which gives you like a 100x performance, and then shifting to egg, like running it in Rust with their better engineering, gives you a 100x more performance boost.
That's
So
pretty cool.
yeah, so the algorithmic gets you 100x, and then egg gets you 100x more. Yeah.
So there must be a code written in Racket online, right? Uh,
Uh, yeah. So the yeah. So I believe that it's there inside the Herbie repo. I haven't looked too hard, but they
okay.
claim that it's there.
Okay.
Um, yeah.
Yeah, I would love to run this on Haskell or PureScript AST and
Right.
what it produces.
Yeah. Definitely. It would be interesting to see. Yeah.
Um, there's a lot of chatting on end. You can type it in chat and I can ask the question. I don't know who was asking the question, but you can just type it in chat.
Sorry, can you hear me better now?
Yes, we can hear you now.
Okay, sorry. So my question was on where you said where you could compute the hash and change it from like a quadratic time to linear
Hmm.
time.
Yeah.
Okay, so um, the place where you compute the hash for each of like the nodes. So
Yeah.
is there like a temporary place where you store the hash values before you then make all the changes at once? Like, can you just like explain that part again? I
So
mean, okay.
yeah, so right, okay, so as best as I understand, here's the story. So egraphs as a data structure were originally built for like solvers, for like SMT solvers or SAT solvers, where yeah, where essentially what you would do is to like attempt a rewrite, um, and and then like as soon as you perform the rewrite, you would then like want to actually sort of like inspect the AST for equality or whatever. Yeah. So right, right, and so like when your workload was something like that, um, it made sense that like whenever asked you to sort of like attempt to equate these two nodes together, um, you try to like maintain the invariant of the data structure to actually give you like an O1 equality check, because in all likelihood the solver is then like immediately going to ask, hey, um, like because of this rewrite, what new facts did you learn? And the only new facts a solver cares about is like what things are equal, right? Yeah, so they would sort of like immediately modify all of these, whereas in the case of like an actual compiler, what you'd actually do is sort of like all the rewrites are going to perform like upfront. So what you can sort of do is to like attempt to just batch all of these. So that like the node X is going to be equated like all of these nodes y1 through ym at the same time. Um, and so like you can then sort of start to process these nodes in sort of like reverse depth order. So that X is like the deepest node that you have in the graph like currently. Um, so you start by fixing the SHA of X. And so when you fix the SHA of X, you know that X is equivalent to all of these guys. And so therefore like everybody becomes equivalent in one shot.
Okay, okay.
Yeah.
So basically, you just like group every
Yeah.
set of rewrites and
Yeah.
then just make it as one. So okay,
Yeah,
yeah.
exactly. Yeah. And then after that, now these have no parent, so there's nothing to invalidate. X has a parent, so you now like attempt to fix the parent and you keep doing this.
Okay,
Yeah. So the general algorithm is to process it in like whatever deepest first, and then like go up to your parents or whatever.
Okay.
Yeah,
Thank you.
you're welcome.
Are there any more questions? All right. Thanks everyone for attending. Thanks, Siddharth. This was really great talk. Let's talk on the group
Sure.
to see if
Yeah,
ask a
great.
lot.
Yeah, thanks a lot, guys. This was a lot of fun.
Thanks, Siddharth.
Thanks,
Awesome
bye.
talk.